Welcome to the CoSpace Robot family. Today, we'll be introducing you to CoSpaceRobot GP. CoSpaceRobot is an official platform for both RoboCupJunior Rescue Simulation and RoboCup Asia-Pacific CoSpace Challenge. Please visit our website to find out more.
In this session, we will give you a step-by-step guidance to the CoSpace GrandPrix. We hope it will help you to have a better understanding of the platform and take part in the CoSpace GrandPrix Challenge U19 category.
Line following is probably the most common application in robotics. It is widely used in industries and even hospitals. If a robot can think, the thought process of a line-following robot will be very similar to that of a human being. And that can be simplified into 3 actions: sense, plan, and act. CoSpaceRobot will give you a unique first-hand programming experience in such applications. Let's take a look at the CoSpace Virtual Robot. It is equipped with one color sensor to sense the floor RGB color, which is a short form for red, green, and blue. One gyro sensor to sense the robot's orientation. One ultrasonic sensor to sense the front obstacles. And 6 infrared IR sensors for line tracking. What is the logic behind the robot's thinking process when it tracks a black line? The 6 IR sensors mounted on the robot are like 6 eyes of the robot. When the first left IR sensor, we call it L1, senses the black line, the robot needs to move forward. When the first right IR sensor, we call it R1, senses the black line, the robot also needs to move forward. When L2 senses the black line, the robot needs to turn left slightly. When R2 senses the black line, the robot needs to turn right slightly. When L3 senses the black line, the robot needs to turn left rapidly. When R3 senses the black line, the robot needs to turn right rapidly. This process repeats forever in a loop, and this will ensure that the robot tracks the black line. Let's code a line tracking program in CoSpaceRobot.
For optimal performance, your PC/laptop should meet the minimum configuration. The Microsoft Robotics Developer Studio and CoSpace GrandPrix Simulator must be installed in order. Let's watch a video guide on installation.
Hello, good job. We are almost there. Let's click on the Experience button to see if our computer is compatible with this software. While we are at it, let's also check and see the version of our software. It's always good to have the latest version. Awesome. It seems that our computer is compatible and our software is up to date. And now it's time to activate our software. So there are 3 options: Learn, Compete, and Experience. We're going to click on Learn. FirstSteps, there's a workshop in iCool. Intermediate, there's also workshop in iCool. Advanced, workshop in iCool. So for this example, we're going to use FirstSteps. Alright, we're going to click on Workshop Pack 1. The activation window has just popped out, so please make sure you're connected to the internet and input your account number, as well as your serial code, which is also your license number. So these will be given to you via email, so please make sure to check your email. And also please make sure when you put in your serial code, there are no spaces in the front and at the back, because the serial code is case sensitive. And if you're having trouble with the software, you should right-click on the icon and click the Run as Administrator option.
Double-click CoSpace GP icon on your desktop. Now, choose the level and map, which is also known as the virtual environment. In this tutorial, we will choose Carnival for illustration. To adjust the virtual environment, first, click anywhere in the virtual environment and then press the Q, W, E, A, S, D keys to adjust the 3D view. If you press Shift plus the keys, it will make the movement faster. If you are lost, press Home key. To manual control virtual robot, first, click anywhere on the control panel and then press the 4 arrow keys to move the virtual robot manually. While the robot is moving, you can monitor real-time data from sensors mounted on the virtual robot. Well done. Let's move to the next section.
Double-click on the CoSpace GP icon on your desktop. Now, choose your level and map, which is also known as our virtual environment. For this video, we'll choose Carnival Practice Field. Double-click on the AI button to enter the programming interface. First of all, you will need to create a new project. Click on the New Project button. Please remember to give this program a team ID, a team name, a project name. Remember, once team ID and team name are confirmed, they cannot be changed anymore. However, you can change the project name if you wish. Based on the analysis earlier, we now need to convert the logic into code which the robot can execute. The first statement should tell the robot that when L1 senses the black line, the robot needs to move forward. Step 1. Create a statement named L1 senses black line. Step 2. After the statement name is defined, we'll add conditions to this statement. We'll click on L1 until it turns black in color. Now this means L1 will sense for the black line. Step 3. We should tell the robot what to do when the condition is met. In this scenario, the robot should move forward. That means both wheels should have the same speed. Step 4. Finally, click on the Preview button to see whether you have set the correct wheel speed. Great! We have completed our first statement. Repeat the 4 steps above to complete statements 2 to 6. Statement 2. When R1 senses the black line, the robot moves forward. This is similar to statement 1. Make sure we have set the same speed for both wheels. Statement 3. When L2 senses the black line, the robot turns left slightly. This time, we will set different speeds to the left and right wheels. As the robot turns slightly, the speed difference should be small. Same concept applies to statement 4. This time, the robot turns right slightly. Statement 5. When L3 senses the black line, this means that the robot is almost off track. So the robot needs to turn left quickly. This time we can set the left motor speed to be negative and keep the right motor speed positive. The same concept applies to statement 6. This time the robot should turn right quickly. After we have completed our program, we should do a quick check that the logic is correct and make sure every statement has conditions and actions. Once you have completed programming, it is very important to save and build. Save means to save the most recent program that you have just completed. Build means to check for syntax errors, create a C code and a dynamic data link file with extension DLL. Now you can click on the trial run button to see how the robot will behave. If you wish to modify the program, click on the stop button and you will go back to the AI panel to modify the program. You can load the DLL file and monitor the robot's performance in the control panel. We can use the play, pause, and stop buttons to control the robot's movement. We can also change the viewing perspective from the menu bar. The AI camera gives a helicopter tracking view or a bird's eye view. The front camera gives a driver's view or a first-person view. We can also put together multiple viewing windows, and a common practice is to keep the overview in the main window and set the front camera in a small window on the side, so you can take a look at details as well as have a good overall picture of what's going on. When the robot reaches the finishing line, it stops, and the time it took to reach there will be recorded. Well done! You have completed the line tracking robot program.
System allows users to add self-defined variables. For example, let's add a new variable, CoSpace. Set the initial value to be 0. Now the new variable, CoSpace, is added. You can also remove the existing variable. This is the basic line tracking code. Using the advanced condition to set all IR sensors conditions. Using the advanced action to set wheel speed and LED status, and adding a printf statement to print out the live value of all variables. Let's work on the challenge 2. You should launch the challenge 2 field. The task for Challenge 2 is to program our robot to travel towards the destination. During its journey, it must stop at each waypoint for 2 seconds with LED flashing, and then move away from the station autonomously. We use duration to control the robot's movement. The duration is a countdown counter. 1 duration equals 0.025 second. We will specify a period of 2.5 seconds. The robot will stop for 2 seconds and then move forward for the next 0.5 seconds. When the robot senses orange color, wheels stop for 100 durations, which is 2.5 seconds. The duration countdown counter begins. It will decrease by 1 every 25 milliseconds. When the duration is 19, which means 2 seconds later, the robot will move away. We have defined 3 variables here. Based on the information received, the robot needs to make correct decision. The virtual robot for U19 has a gyro sensor. It senses robot's orientation. The strategy of making 90-degree turning is to let robot keep turning. When the remainder of compass value divided by 90 is 0, it means the robot has just turned 90 degree. Well done. Let's move to the next section.
RCAP CoSpace GP Challenge Rules U19 category. This category is for students aged 19 and below. Welcome to the RoboCup Asia-Pacific RCAP CoSpace Challenge. Automation of routine tasks is currently a concept that interests many industries. Among the most revolutionary parts of it are autonomous vehicles. These are visions of the future of city infrastructure. The main ideas they all share are self-driving cars and shared mobility. Those are set to revolutionize the ways we navigate through cities. In CoSpace GP Challenge, teams are required to build a real robot, develop and program appropriate strategies for both real and virtual autonomous robots to navigate through both real and virtual worlds. For the iCool Challenge, participants need to program an autonomous car to navigate in a smart city. The autonomous car needs to pass multiple waypoints before reaching its final destination. In this smart city, there are roads, buildings, color markers, black and white lines, ramp or bridges, APRO tags, and waypoints. In the iCool Challenge, there will only be a virtual robot. The robot has an IR sensor array, an ultrasonic sensor, a RGB color sensor, and a gyroscope. Students need to utilize the elements in the smart city to plan the best path and program the robot accordingly. Let's take a look at the game process. The duration of the game is 8 minutes. That means the robot has to complete the whole journey within 8 minutes. At the beginning of the game, the virtual robot is placed at the start station. When it travels towards the finish line or end station, the robot must pass all waypoints in any sequence. It must stop at each waypoint for 2 seconds with LED flashing, and then move away from the station autonomously. The game ends when the virtual robot arrives at the finish line in the virtual world. If the virtual robot passes all waypoints and reaches the finish line, the team rank is determined by the race time at the finish line in the virtual world. If the virtual robot is not able to pass all waypoints, regardless whether it reaches the finish line or not, the race time for the virtual robot to reach the last waypoint will be recorded. The team rank will be determined based on the number of waypoints passed, followed by the race time.
The detailed rules can be found in RoboCup Asia-Pacific official website. If you have decent experience with programming or have completed CoSpace GP FirstSteps or are above 12 years old, CoSpace GP U19 is designed for you. There will be one video in this sharing and highlighted games section.
Everyone, I am Liao from Singapore, participating in the CoSpace GrandPrix Challenge U19 category. I started doing robotics in March this year. While programming my robot, I used 3 different strategies. The first one is path planning, which is used to decide the best path to take. I screenshotted the map and drew out several possible paths, considering the pit stations, color markers, the number of turns, and distance, as these factors can significantly affect the speed of the robot. After deciding on the best route, I will still make minor changes to the path to achieve greater stability. The second strategy I used is soft coding, where I create functions that will be called upon to carry out actions when certain conditions are met, and also variables that can help to keep track of the position of my robot on the map. This is especially useful for actions that need to be used repeatedly. The examples are line tracking, turning when facing the wall or detecting certain colors, U-turns, and stopping at the pit stations. Last but not least, I used hardcoding, as my roads included some shortcuts that do not provide any sensor inputs for my robot. To achieve the optimum output, I did multiple runs and measurements. Through the process of trial and errors, I was able to obtain some values for me to directly write into the codes and let the robot run a designated road without sensor inputs. In preparation for CoSpace, I tried out all the practice maps. The first two maps looked manageable. However, when it came to the more difficult maps, I encountered problems sometimes, even when I followed the tutorials step by step. I started considering more possible scenarios and tracking the values in debug to adjust conditions or add on more statements, such as color range and more cases for line track. These changes made me realize what worked in theory will always need to adapt to fit the physical environment, and I must consider many other factors to make sure the car not just runs, but runs consistently. To challenge myself further, I attempted to code in C, which is a programming language I have never learned before, and implementing proportional integral derivative control on line tracking parts of the robot. I never truly understood or coded PID before, but CoSpace gave me the chance to grasp this concept firmly. Even though I didn't get to use it in the preliminary round due to instability of high speed, the experience of learning it is rewarding beyond what I can imagine. It taught me to be resourceful, search for answers on different engineering websites and ask a mentor. It taught me to have perseverance, debugging again and again to make sure the codes will run smoothly. It taught me patience. The best values can only be obtained after a tedious process of tuning the PID. In addition to technical skills, I also learned the importance of communicating and sharing ideas with my mentor and fellow participants. Through good communication, we improved faster, solved problems more creatively, and rejoiced in progress together. A participant I would like to learn from is SG3020, John Henry. He mentioned in his presentation video that he used different speeds for different parts of the map and also increased turning speed. These are things I did not think of when programming my robot, and I think that these are certainly important factors that can make a remarkable difference in speed and timing. With this enriching experience, I will share my learning with my fellow members from the Robotics Club who will be participating in virtual RoboCup Asia-Pacific GrandPrix as well.
And we're off! The robot has left the starting point. And we have passed our first waypoint. Wonderful path planning. Second waypoint. Keep going. Third waypoint. Nice U-turn, so much time saved. Wonderful path planning. Fifth waypoint. Nice U-turn. Wonderful path planning. Keep going. Fifth waypoint. Sixth waypoint. Nice U-turn. Wonderful path planning. Awesome. Great turn. 7th waypoint. Awesome. Wonderful path planning. Great shortcut. Keep going. Nice U-turn. Last waypoint, almost there. Keep going. And we have crossed the finish line. Great job! Congratulations! Challenge completed.
After finishing CoSpace GP U19, why not try CoSpace Rescue? Like to view more sharing and game videos? Visit RoboCup Academy YouTube channel.